Okay, let us begin our seminar. Before we start, I would like to introduce you our first, and hopefully not the last, postdoc, which have appeared in our group. So this is Dr. Tang. I can ask everybody to assist him because he's not Russian, he's not from Russia. So it's very important to get him accommodated as fast as possible. So please assist him if he has any problems, if he has any requests to you. And now I'd like to introduce our speaker. So this is Kirill Nekludov, our PhD student, who was the first author of a recently accepted our NIPS paper on further extension of variational dropout for so-called structured pruning, Bayesian pruning, right? Via truncated or normal noise on the activations of neurons. So this was one of the two NIPS papers from Russia. Another one was by Anton Osokin, who had already told us about his paper. So this is the second paper from Russia to NIPS. So Kirill, please.
Thanks for introducing. Today I'm going to tell you about our recent results on specification of deep neural networks. Work with Dmitry Molchanov, Arseny Ashucha, and Dmitry Vetrov. It's called structured Bayesian pruning via log-normal multiplicative noise. And let's begin. What is structure sparsity and why do we want structure sparsity? Of course, here's a simple picture describing it. That we have assume we have some matrix of weights. And when we have unstructured sparsity, it's just randomly dropped weights. And when but we want we want our sparsity to have some structure. So in this example, we drop rows. And that provides us with acceleration of deep neural networks and more efficient compression. And one of the some applications that's small feature representations, which can be used for example, for image retrieval. And there are a lot of related papers, a lot of works, but they all concentrated about one main idea, group lasso, introduced by these guys, Ming Yan at 2007, and here you can see just standard objective for linear regression with mean squared error and group lasso regularization term. And also we can add some other regularizations if you wish, and that's one common idea. But there are several flaws, and this idea we have.
Is it L2 or L1 norm? I always said that in last there is L1.
L1, L2.
Yes.
Yes, that's L1, L2.
L1
that's just
group-wise, L1 norm.
It's L2.
It's L2.
No, L2 is squared.
No, that's like squared is not norm.
Yes.
This is the norm.
But it is a special case of...
This is L2, L1, L2 norm. What's the problem?
No problem.
Because on the blackboard, the formula is incorrect.
Okay. There are a lot of hyperparameters, and that's objective not smooth, and that's why we decide to do some Bayesian method. As always, we have to find some posterior distribution over our parameters of our model, using likelihood and prior distribution on our weights. but we as always have intractable integral in denominator, and for tackling this problem we use one of the famous techniques, variational inference, where we approximate true posterior distribution by distribution from simple parametric family. So this distribution on slides Q and with parameters phi. And we can rewrite it as this. We have a new formula where we need to minimize chiral divergence between approximation and prior distribution. We need to minimize negative expected log likelihood and some constant with respect to phi. And as long as it is constant with respect to phi, we can see this as our new objective and minimize it. But we also can somehow estimate expected log likelihood, and we estimate it using Monte Carlo estimation, where we have some batch of our data. So in deep learning, you I think all knows what is batch of data, and we sample our noise already reparameterized. And we estimate our expected log likelihood as this sum, and now we can calculate all this thing. Actually, we can backpropagate through this thing, and we don't need to minimize it as it is. We just need to compute gradients. So that is stochastic variational inference, and in more general, we can add some non-random parameters. In our case, that will be weights of deep neural networks, and optimize both with respect to phi and W capital. Now let's move on to our model. So structured Bayesian pruning, I remind you, and let's look inside our neural network and see how our model can be implemented. We just take output of some layer, for example, dense layer, multiply each coordinate of output by some noise Wi, and pass all this stuff to the next layers. So I think it's clear. And why do we do this in this way? We want our Wi, so our noise, be near to 0. So when Wi is 0, we just can drop this connection, drop neuron, or drop filter for convolutional layer. Okay. To define our model, we need to define a prior distribution. That's just independent distribution for each Wi. And Wi distributed log uniformly. And we also need why we need this prior, because we want push our Wi close to 0 to remove some neurons.
So why do you call your model structured pruning? Here you have just separate weights, they are absolutely dependent. Where the structure is?
The structure is when we apply noise to the group of weights. In this case, we apply to the one neuron, so we apply to the row of dense layer matrix.
So one more question, and is this like the only difference to the previous technique, like from ICML? So basically, before, like, these W's were actual weights, and now W's are positioned differently. There are more differences. Like
There are more differences. One more difference is variational distribution is. And there we don't have, no, it doesn't matter. Okay, for our variational distribution, we choose log normal distribution. Also, it's independent on all the coordinates of our noise, and that is just such random variable. Logarithm of that is normal, and that's all. And why we choose log normal distribution? First of all, there are no prior gap between a log normal distribution and log uniform distribution. So log uniform distribution can be seen as a special case of log normal distribution when sigma is set to infinity. Secondly, we have only positive multiplications. Let's see. Here we have wi only positive, and also we should choose likelihood or variational distribution that can be that should be defined on positive numbers. Compared to Gaussian dropout, where we have multiplicative noise, also multiplicative noise, but from normal distribution, during the train we can multiply our inputs on some negative numbers or positive numbers. But when we use ReLU for nonlinear activations, we multiply our inputs on the test stage only on positive, only by positive numbers, and that is bad. And in our model, we have only positive multiplications. And thirdly, Kirill divergence can be computed analytically, and that's also pleasant for us. But this model has some problems with improper prior. Let's try to derive a Kirill divergence for our model between variational distribution and prior distribution. Let's prove this equality. Okay, assume. Is it obvious, or I should prove it?
No, I think you should
Okay.
derive a couple of formulas.
So now Kirill wants to prove that Kirill divergence is independent, is invariant with respect to bijective transformations.
Yes. Yes.
That's quite an important property of Kirill divergence.
Assume we have some random variable psi, and it has PDF p of x and CDF f of x, f capital of x, and now we want to obtain PDF for random variable eta for f of psi, and let's define it like this, and I think it's that's pretty obvious, I think, because we can derive it using definition of CDF, and thus we have x, and that equals to p of f minus 1 of x. So is it clear?
Well, your formula is true only for
Yes, if
bijective, monotone, and non-decreasing transformation, and one dimension.
Yes. But we have logarithm, so it's true.
And if the
If inverse function exists.
this means that the transformation is bijective. That's true, but why should it be monotonic?
Because otherwise the derivative would be negative.
Well,
not-
we
it has
can
to be increasing.
we can use a decreasing transformation, but
Yeah,
in
but
that
you just
case
need
we
to
should
account for the sign.
put an absolute value for the equivalent.
Mhm.
But anyway, it should be monotonic.
If it's not monotonic,
It's not monotonic.
it's not inverse.
So-
Yeah.
There are
So
no
bijective.
inverse
Yes.
functions. So now assume we have.
Well, it can be non-monotonic and bijective. It's like it's discontinuous.
Okay, it's continuous.
So it works only for logarithms, actually. And exponents. It's like this.
Assume we have xi1 and xi2, which is have PDF p of x and q of x, and we have eta 1, eta 2, which is have PDF head of x. Oh. And we want to calculate the divergence between eta 1 and eta 2.
You recommend while you're writing.
Correct divergence. That's the definition of correct divergence. And now we want to use this formula, this result, and because we want to show that this scale divergence between eta 1 and eta 2 is equals to scale divergence between xi 1 and xi 2. So p of x logarithm p of x q of x. Oh no. F minus 1 of x logarithm p of f minus 1 of x u f minus 1 of x and df minus 1 of x dx. And now if we define y equals f minus 1 of x, we see that this integral equals to p of y logarithm p of y q of y and dy, and this equals to curl divergence between xi1 and xi2. So that is what we use writing this formula.
Did you skip the step where you convert P of f inverted to P of y? Because you also need to multiply by df inverted by dx.
Yeah, I just submitted, but
Yeah.
because it's.
Well, but this is the key step. Actually. The Jacobians vanish because they're both in numerator and denominator and the logarithm.
Yes. But I think that's pretty clear because we can just. Okay.
Now, it is as clear as the invariance with respect to monotonic functional transformation itself.
So, teacher's mark is F, remark is DF.
In general, this derivation works for an arbitrary f divergence.
For what?
F divergence.
For F divergence.
Mm-hmm.
So you may replace log with another convex function.
That's a good remark.
I also want to add that the same trick works for multidimensional random variables. The same idea is used in concrete distribution paper, which is Google softmax. So essentially they apply softmax to some random vector, and then for computing KL divergence they don't apply the softmax, and this results in much more numerically stable formula. So this trick is quite general.
Thanks. And then we can calculate KL divergence between normal distribution and uniform distribution, and see that that is some infinite constant c minus logarithm sigma. And why this constant is infinite? That's because we have, because actually we have improper prior distribution, because that's a uniform distribution defined on the all positive numbers, and we cannot normalize it. We cannot normalize this distribution. And this so rewriting it to our formula, we can easily minimize our objective, because we can just set sigma to infinity and obtain optimal results. And of course, it's not good for us, because we don't want our network just output some random stuff because of infinite variance. And how we decide to handle this problem? We decide that we works with finite numbers, because on finite subsets, because computers don't know what actually infinite number is, and we can just limit our subsets of all our distribution, both prior and variational approximation, to some interval from A to B. Then formulas for KL divergence and others become more clumsy, but that's not a problem. They can be computed analytically. So now we have a probabilistic model.
The question, could you show like this clumsy formula? Like, it's very interesting how A and B actually enter the equations. Because like, is the formula super sensitive to A and B?
Like, can you take the limit?
Yeah, maybe like ideally if it didn't depend on A, B at all, then like you just don't care. But like, how bad is it?
Okay. The formula for KL divergence is later I'll explain this notation. And minus where sigma I mu I be a parameters, and phi of x CDF of standard normal distribution, phi capital. Phi of x is PDF of standard normal distribution. Beta equals to b minus mu I divided by sigma I, and alpha is this almost the same.
And I'm going to use just general A and B, not just 0 and 1, for instance.
You can use, no, we don't train A and B, we can use, that is hyperparameters of our model, and we can choose it almost arbitrarily, but in our work we find best values for A and B.
So you actually like choose them, you cross-validate them, and like it's better which
yeah.
So had you tried different values? How sensitive is the method to?
Actually, if you see at log normal distribution, you will see something like this, and that means that most of the times you sample your value, noise value, you get something small from here, and very rarely you have some huge noise. That can be very bad for our deep neural networks because it crushes all the weights, all the gradients, and that's why we choose B small, for example 1 or 2 to live here, and A we choose approximately we choose something very small, about 10 minus 10. I don't remember. That's a good question. Actually, you can set it to 0, but we derived all the stuff for truncated distribution. I think that the same works for.
You will set a to 0. This will mean that in the usual scale it will be minus infinity. And that will be bad because our prior distribution will become improper. So we have to limit the left bound. Otherwise, walk uniform distribution.
Yes.
Walk uniform distribution.
No.
If we set a to 0, it can be normalized. And this means that infinite amount of probabilistic mass is concentrated at 0. This is bad. This is exactly what we would like to avoid.
But like on this picture, there is no infinite mass at 0. It's log normal.
This is log normal. And prior distribution is log uniform. And log uniform distribution can be normalized if we set a to 0. So we should set a to very tiny value, but not to 0. Then we can normalize it.
And A and B should be the same for prior and posterior.
Yes.
Yeah, because like
So.
But if you set A to like super small, 10 to minus 10, then it's like essentially if you take log of this, you'll get infinities. So it's kind of like essentially infinity. It's very small numbers.
But still not infinity.
You don't
We may normalize both distributions.
Why not take like 10 to minus 100?
You can.
You can. So actually, the answer how to set A and B, probably the best answer, we set them due to numerical stability. So we found the best values which are the most stable. We can set B larger, we can set A smaller, but the method will be less stable. So the result should be the same, but
In which operation, like, so I guess it's numerical stability of KM computation or in derivatives?
I guess
not only in derivatives. When we inject some noise, for example, we set B to large values, just like Kirill said, we can sometimes obtain extremely large noise. And this noise will destabilize our training procedure.
So it is like in some sense equivalent to gradient clipping.
Well, there's probably you can make this analogy, but well, quite indirect.
And so what is the case when we prune our weight? If mu is 0 and sigma is 0, or what?
That's next slide.
Kirill, please continue.
Okay. To define whether we need to prune our group or not, we calculate signal-to-noise ratio. That's the ratio of expectation and standard deviation. Here we have example with, so what is good and what is bad? Signal-to-noise ratio 3 is better than 1 or not? Yes, because we have lower standard deviation compared to our expectation. But here you have example of two distributions, one with signal-to-noise ratio 1 and one with signal-to-noise ratio 3. So we take all the noise coordinates, we calculate signal-to-noise ratio, and drop all the coordinates with a low signal-to-noise ratio, defining it by just threshold, you know, and that's our pruning method. Okay. Now let's move on to experiments.
Sorry, where is the Bayesian procedure of automatic tuning of everything and automatic pruning? You use some thresholds. Well, why not to just adjust all this mu and sigma?
Adjust.
Using your variational inference technique. And come to some zeros here.
And also set a prior on A and B and do. hierarchical inference.
There are many variants to do, but not to introduce some artificial thresholds with signal-to-noise ratio.
So what's the question?
Where is the Bayesian procedure?
There are no Bayesian procedure. We can tell that stochastic variational inference Bayesian procedure. Okay.
But like when you do your pruning, do you know what happens with your with your lower bounds? Like, do you have any guarantees, or like it's all lost at that stage? It all becomes like empirical.
Yeah.
And the threshold is 1, yes?
Yes. So now let's move on to experiments. If we remind variational dropout or other dropouts, we know that we fix means and train only sigmas. But here we decided to train both sigmas and means, and that's improve our low bound and provide us with good sparsity. Also, we have some results for MNIST dataset for fully connected linear and convolutional linear, and on the first rows of both sides you can see original architecture dense, and on the last rows you can see our results on this architecture, which we compare with structured sparsity learning method and sparse variational dropout. And you can see that error almost the same, but we have greater speed ups in CPU, GPU, and floating point operations per second. Also, we can build such mask where we can show importance of each pixel on MNIST dataset. Black pixels is important pixels and with high SNR, and white pixels is irrelevant pixels with low SNR, and we have such mask. Also, we have results for VGG architecture. Here you can see in blue bars for each layer of the network number of neurons or filters, and in orange bars resulting sparse solution. But it have no great speed up because all the computation time concentrated in the first 5 layers. Then we decided to just weight our KL divergence. So for the first layers, set more penalty, and that's provide us with more fast solution, but also with a little bit accuracy loss compared to initial architecture.
Excuse me.
Yeah.
Have you any ideas why you have so much sparsity on the 10th layer? I use?
So much sparsity on 10th layer?
Yeah. It looks like bottleneck.
Maybe. I think that's true about all the last layers.
No, but this 10th layer is somewhat specific. So this is really bottleneck.
Yes.
We have just 9 neurons, and these results are very reproducible. So they're not dependent on initial approximation, on a particular shuffling of training data. So there's something in it. And this means that final classification is fully defined by just 9 numbers, just 9 nonlinear functions of initial images. And this is quite interesting.
And there are 10 classes in CIFA 10.
Yes.
But here are just 9 neurons. So the number of neurons is less than the number of classes.
Not really 9
And we're
because
still not losing accuracy.
our picture is 2 by 2 and has 10 channels. So it's 40 numbers.
So it's 9
Several-
feature maps.
It's 9
Ah,
feature
okay.
maps and picture size is 2 by 2, so not
Okay.
not so much.
And when we decide to increase our architectures, just increase the width of each convolutional layer and each dense layer, and we see the very similar picture. So we can, if we compare each layer by layer, we can see that most of the layers are very close, and we can discuss it like our model find optimal architecture for this task. And one more experiment for random labeling. That's about a recent paper from ICLR where generalization needs rethinking, where people show that standard regularization techniques cannot prevent overfitting. So we have lineate 5 with binary dropout, but it achieves on MNIST accuracy about perfect accuracy and of course random guess for test. But our model just prune all the filters and provides us with trivial solution for there are no network, no filters, no groups, everything is 0. So that can be seen as regularization ability of our model. Read our paper. We propose structure sparsity model for acceleration of deep neural networks. We propose proper probabilistic model, and it can be seen as just separate dropout layer that's easier to apply to other models. Thanks.
So any questions? Yes, please.
Could you please summarize briefly your procedure for achieving this structure sparsity?
For achieve structure sparsity,
Yeah.
how I can summarize it, I don't understand.
Like, you told us quite a lot, so could you please tell us briefly what's your method? Like,
How
from
to
one to the
implement
other.
it?
Yeah.
What does the layer look like?
Layer look like?
What does the layer look like?
Okay, it look like this. That can be seen as a separate dropout layer that you can in place in any network, and it removes some groups of weights. For example, neurons for dense layer or filters for convolutional layer.
Thanks.
Another question. So I see you have like two, like starting from the ICML paper, you have two changes. One change is going from like dense layer, like from priors directly on the weights to like this, like the structured weights, and then there are changes in priors and like all the log normal business.
Yeah.
So what will happen if if you do like just one of the steps? So like first to just go to like structure sparsity and like use the same priors as before. Or like vice versa, if you apply like log normal business to the weight directly.
The same
Can this be
prior.
done?
If we use, if we take model for structure sparsity and use prior for as before, as in ICML paper, we have problems with improper prior.
And then like, and before improper prior, there were no problems. So
There are other
why problems start to
variational
happen?
approximation. We
But
use,
like, can't
we
you
use another variational distribution.
But like, can't you use the same variational distribution? It's just like you have a neural network and you are adding dropout, but just like on different parameters. So like, why you cannot just change this and apply it to a different one? What's the? I don't quite understand why do you need to go like through.
I think this will be. I think that can be equivalent because we just can reparameterize our model and show that in ICML paper that's also multiplicative noise, but with multiplicative noise with normal distribution, but with non-parameters.
But have you tried like just doing less work, just take HTML tape and just do the same thing but change the parameter, apply it on the different parameters, or it doesn't work, or like what happens?
Yeah, we did try it, so it was much worse.
And we also tried.
And so basically, if you apply this, then the new price on the old model, does it still work? Does it help, or like what's the?
This prior to
This
the
prior
old-
on the old model, just on the weight directly.
We have problems with reparameterization trick because we need to sample every single weight. We cannot just write it like sum of log normal distribution.
You mean you can't like local computational, you can't use local
Yes,
computational
because
it's very slow.
Okay, and apart from being slow, is it like you just cannot try it at all?
It's
Like,
very
is it, like,
slow.
it's very slow?
Very slow.
But like on the big GPU, like
No,
So it's almost
even on
impractical.
GPU.
Impractical.
even like on like a tiny network.
Yeah, I think on that
Like
tiny
MNIST?
network-
How tiny it should be?
MNIST?
10 neurons per layer, maybe then it will work, but it's useless.
It's very
I would also say that in this model, what is good is that we can compute curl divergence in a closed form, unlike the previous model where we could not, and we had to deal with some numerical approximations.
Okay.
So this is a bit more elegant solution.
Yeah,
It doesn't matter, but they're still
But
closed form.
then like, why is it slow? Like what is the slow piece? So it looks like
I
a
don't know what is local computational.
So,
Yes.
And here you can't view it. So you need to sample not one noise per neuron. If you use log normal distribution for each weight, then you need to sample not one noise for each neuron, but one noise for each weight. It's quadratic. It's very
So you
slow.
sample not 2D
Yeah.
noise, but 3D noise, three-dimensional noise.
okay.
It's very small.
3D if you like have several elements in the bunch, several objects.
Okay.
And in the previous model, they used local computational trick, and they didn't. They did not need to do it. To denoise.
Okay.
any more questions? Yeah, like, go please to the MNIST results slide 2017. Yeah, could you please comment on the low GPUs deducted in the top part?
This.
Yeah, why?
I think that because architecture is pretty simple, that's really small.
Like it doesn't use GPU at all. So why?
Almost.
Actually, I guess that's supposed to be the truth. Like on the net, you don't really need GPUs.
That is only two layers with 15 neurons and 500 neurons and 300 neurons. Two dense layers.
Yeah,
And that's all. So two matrix multiplication, that's not a big deal. That's all.
Okay, yep. So let us thank the speaker. And I would like to add that this is another example that shows that current deep neural architectures are redundant. So and we can remove at least some redundancy by using some kind of Bayesian inference inside deep neural networks. So here is the redundancy. Here we would like to exploit some kind of structured sparsity, so the sparsity rate was much less than when compared with the variational dropout. But the sparsity is structured, and this means that we were able to accelerate the inference time in deep neural networks, unlike the case with variational dropout, when we can dramatically compress the network, but we almost cannot accelerate it. And that's interesting. In both cases, we used log uniform prior distribution, either over the weights or over the activations. But of course, we should understand that we can use different prior distribution, and then we'll end up with different effects on Bayesian neural networks. So here in both works, we wanted to obtain some sparsity. So we use some sparsity promoting prior. But we would like to get, say, for example, rich ensemble of deep neural networks. Then you probably should use different prior distribution. You will not get sparsity, but you may get a rich ensemble, which will potentially allow you to improve the accuracy even further. So this means that when we work with Bayesian neural networks, and probably many of you will do, at least who are under my supervision, we should always keep in mind what we would like to get, and based on this, we need to understand which prior distributions we should use over the weights or observations or what.